Recent dynamic radiance field works enable photorealistic free-viewpoint rendering experience. However, they are restricted to short sequences without changing motions and offline rendering. To fill this gap, in our work, we propose neural residual radiance field (REF), a novel neural representation to support streamable free viewpoint viewing of dynamic radiance field. REF enables to achieve a high compression rate while maintaining high rendering quality. Also, we developed a REF-based codec and companion FVV player to stream dynamic radiance fields of long sequence with large motions. Now first let me show our REF-based codec and a companion FVV player. It enables long-duration FVV online streaming. Users can browse the dynamic radiance fields online like viewing 2D videos on streaming platforms. During the playback, our REF player allows users to freely choose their viewpoints. Users can also pause the screen to generate static bullet time viewing effects. When the play button is clicked again, our user can continue playing. Benefiting from the design of our graph structure, our REF player allows fast seeking to a new position to play during the playback. Our methods also allow multiple users to experience photorealistic free viewpoint videos of dynamic scenes online at the same time. In summary, with REF, a user for the first time can pause, play, fast forward, backward, and seek on dynamic radiance fields as if viewing 2D videos, resulting in a high-quality free viewpoint viewing experience. Now first, let's go to our system overview. We use our sequential training scheme to generate compact REF representation with motion grid MI and residual grid RI for each frame I. And next, our REF-based codec scheme and player will compress it to enable fast data transport and online playing. And now this is our neural residual radiance field REF detail pipeline. Given a well-trained feature volume ft-1, we first estimate a dense motion field dt, and next we'll generate a compact motion grid mt through motion pooling. Finally, we will warp ft-1 to a base grid ft hat and learn our residual grid rt to increase feature sparsity and promote compression. And to make our REF practical for users, we need our REF-based codec and a companion FVV player. Here, we first divide the feature grid sequence into several continuous groups of feature grids. We call it graph. Graphs are comprised of an I feature grid, which is the keyframe, and the P feature grids. I feature grid, which is coded independently of all other feature grids. And each P feature grid contains a deformable compensated residual grid relative to the previous feature grid. And now let's go to the detailed architecture of our REF-based codec scheme. Mainly contains two parts. The encoder is in green and decoder is in pink. When the signal is input, we will first judge whether it is keyframe or not. If it is not, an additional PCM module is needed to further compress the residual feature grid. And then, each channel of feature grid Fi or the residual grid is divided into cubes of 8 times 8 times 8 voxels, and each cube is separately transformed by using a 3D DCT. After that, the transformed coefficients are quantized using a matrix. Quantized transformed coefficients are entropy coded and transmitted together with other information such as motion field MT and frame type. And when the bit string is received, it will first entropy decoded into the quantized transform coefficients. And this data will be first reconstructed by performing inverse quantization and 3D inverse DCT. And then it will also judge whether it is keyframe or not. If it is the keyframe, it will directly send to the render. If it is not, it will go through the inverse PCA to get reconstructed residual grid, RT head, and we will use the decoded motion field MT and previously reconstructed feature grid FT-1 to obtain the predicted current feature grid FT by deformation. Then it will be sent to the render. And finally, let's see our compression result. Compared to the frame-to-frame training methods, we can achieve similar quality with much smaller frame sizes. Other dynamic methods usually fail due to the topological changes and limited network capacity. All methods also support variable storage sizes.